Hello and welcome to this revision session for Paper 1 in AQA A-Level Physics. So in today's revision session we're going to look at how to answer examination questions on A-Level Physics Paper 1. So if we've been successful and we've learnt in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for AQA A-Level Physics. So how should you carry out this revision session? Well, when completing this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the questions in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful and any hints and tips on answering questions from this revision session. At the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you revise AQA A-Level Physics? So the first step you should be doing is you should be looking at the knowledge, so learning the key facts. So use revision guides, class workbooks, student prep notes, the textbook to learn the key ideas of the course, such as making mind maps and writing out the notes yourself. Then you should be testing yourself, so use the Caboodle platform, use Seneca, use student knowledge checkers to quickly test your knowledge, and you can do this from your own cue cards. The third step is then practicing, using exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you may wish to download past exam papers to do this. So you should be revising A-Level Physics by learning the key facts, testing yourself and then practicing examination style questions. So let's now have a look at some questions for AQA A-Level Physics Paper 1. So the first topic we're going to look at is particles and radiation. So an isolated metal plate is given a negative charge. Electromagnetic radiation is instant on the plate. The plate loses its charge due to the photoelectric effect. Discuss how the rate of loss of charge of the plate depends on the frequency and the intensity of instant radiation. In your answer, explain why the plate loses its charge. The photoelectric effect occurs only for frequencies greater than a particular value, and that the rate of loss of charge increases with the intensity of radiation above that particular value of frequency. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that what you've got to do in these types of questions is ensure you answer questions in a coherent order and structure, and also answer each bullet point in the question that's given to you as a separate paragraph. So what you should be saying is that for area A you're going to lose its charge because emission of electrons from the surface when the electromagnetic radiation is instant on the plate. Okay, so therefore the number of surplus electrons remaining on the plate will decrease with time, so therefore the negative charge will go down because the electrons emitted will carry the negative charge away. In terms of the frequency, we know that from the second question, why is only occur for frequencies above a particular value? Well, the minimum energy required to liberate the electrons from the atoms from the metal surface is required, and that is the work function. So a photon must be supplied to produce this, to give the electron its energy in a one-to-one interaction. So the energy of a photon, so therefore the energy supplied to the electron to be liberated, is equal to hf, and therefore the minimum frequency required is going to be our threshold frequency. You can see how it's important that we learn the key terms to do with the photoelectric effect. Then in terms of intensity is how many photons hit the surface every second. So this tells us that the intensity increases, more photons hit the surface every second at the same energy, so therefore we've got to increase the number of photons per second even if the frequency increases, so that gives us more electrons released from the plate every second, so the charge will go down more rapidly. The next question says, charged particles are emitted from the metal plate with a maximum kinetic energy of 1.1 eV when radiation of frequency 1.2 times 10 to 15 Hz is instant on the plate. Calculate in EV the work function of the plate. So pause the video now, then unpause the video when you want to go through your answers. Right, this question is testing you on how you can A, use the photoelectric effect equation, but also how you can convert EV into joules and vice versa. So what you've got to do is say what's 1.1 EV in joules. Okay, so you do 1.1 times by 1.6 times 10 to the minus 19. What we can then do is work out what our work function is going to be by doing by saying that the work function is equal to the energy of the photon minus that kinetic energy. Now the energy of the photon is equal to hf, so it's the Planck's constant times by 1.2 times 10 to the 15. So therefore you work it through and then you get that energy in joules. But it wants the energy in EV. So what you then got to do is you've then got to divide your answer by 1.6 times 10 to the minus 19. So what you should be getting is 3.9 EV, because you work it through and you work out what your work function is, and then you divide it. So you work it through and then you can divide it by 1.6 times 10 to the minus 19 to get 3.9 EV. The next question says, Figure 4 shows apparatus used to demonstrate the wave-particle duality of electrons. So the heated filament emits slow-moving electrons. In region P, the electrons are accelerated to a high speed. At Q, the fast-moving electrons are instant on the graphite target. R is a point on one of the bright rings that are formed where the electrons strike the fluorescent screen. The electrons demonstrate wave-like and particle-like behavior as they travel from the filament to the screen. State and explain in which of P, Q, or R the electrons are demonstrating wave-like behavior. The apparatus is adjusted so the electrons are instant on the graphite target with a greater speed. Explain why the bright rings formed on the screen now have a smaller diameter. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important you understand what's particle behavior and what's wave behavior. So Q is going to be where it's acting as a wave because it's diffracting out, and diffraction is a wave property only. Okay, so it's very important you understand that idea. So the diffraction is because the electrons move between the layers in the graphite, therefore they then spread out between the layers in the graphite, so diffraction is taking place. Now, why will the bright fringes form here? Again, it's very important you know that when we're doing wave-particle duality that we use our equation for de Broglie. So therefore we know the de Broglie equation for wavelength is equal to h over mv. So therefore we've got a decreased wavelength, and therefore the momentum of the electrons will increase to work it through like so, because if lambda is going down, well then mv has to go up from our equation because h is a constant. So therefore less diffraction occurs because there's a shorter wavelength now relative to the layers in the graphite. Now remember again that diffraction occurs when the gap and the actual wavelength are approximately equal in size. So now one is changed dramatically, they won't be approximately equal, so you won't get as much diffraction, and there that gives you your answer. The next question says, a sample of bromine gas contains a mixture of two isotopes. An experiment is done to find the percentage of each isotope in the sample. In the experiment, the gas is ionized by a beam of electrons. Explain how the beam of electrons causes a particle of the gas to have a charge of plus 1e. So how would you work that through? So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, an electron in the beam will collide with an electron in the gas. So what will happen at that point is when the electrons interact, there will be an energy transfer between them. So it's a bit like the being excited. So an electron in the beam will transfer some of its kinetic energy to the electron in the gas particle. So as a result, that will cause excitation. And then what will then happen is one electron will then leave that gas particle and work it through like so. The next question says, bromine has a proton number of 35. The two isotopes in the sample have different nucleon numbers. Calculate the number of neutrons for the isotope that has a greater nucleon number. Then deduce the percentage of each isotope in the gas and justify your conclusion. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? So you find the nucleon of the more massive isotope. So we know that, for example, that the proton number is 35. So we then do 162 divided by 2, which is 81. So therefore what we can then do is we can then work out our values like so. Then we do 100, or we could do 162 minus 70. So 2 times by 35 is equal to 92. We can work it out and we get it to be 46. Now what's the percentage of each isotope going to be? Well, the percentage is the same for both isotopes. So each isotope makes up 50% of the gas by number. So therefore what you can therefore say at that point is that 158 is made up of 2 atoms, the lighter isotope, and 162 is made up of 2 atoms, the heavier isotope, and the percentages are both 25% in the same ratio. So you could also indicate that half of 160 is made from the lighter isotope and all of 158 is made from the lighter isotope, and that gives you 50%, and therefore half of 160 is made from the heavier isotope and all of 162 is made from the heavier isotope, which again is 50%, indicating that's 50 and 50%. We're now going to look at some questions regarding waves. So, two transparent prisms A and B of different refractive indices are placed in contact to produce a rectangular block. Figure 12 shows the path of a ray incident normally on A, refracting as it crosses the boundary between the prisms. Firstly, explain how the path of the ray shows the refractive index of A is greater than the refractive index of B. So pause the video now, then unpause the video when you want to go through your answer. Right, well, how do you answer this question? Well, if you look at the diagram, what you'll notice is the angle of refraction is greater than the angle of incidence. So if you look on here, if you look at your different angles, you can see that's going to be taking place, and you can actually use that from your similar triangles to work that through. Or you could just say fundamentally that light is bending away from the normal when it speeds up, indicating that the refractive index of A must be greater because it's travelling faster in B. The next question says, show that the angle of refraction of B is about 60 degrees and draw on figure 12 the path of the ray immediately after it reaches P and justify your answer with calculations. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you can see what the angle of incidence is, and remember the angle is always from the normal, okay, to the ray, so it's not going to be 43 but 90 minus 43, which is 47. We can then use Snell's law to then work out our angle of refraction because we've got the refractive indices of both the objects. You can work it through, so therefore you can say 61.4. Then for the next question we can say that the critical angle is equal to 1 over n. We've got n again, so we can work out the critical angle to be 48. We therefore know our angle of incidence is going to be 76 degrees, so therefore it indicates that the ray is going to be reflecting off P to land on the top of where n is on the not to scale label when it meets the glass surface, because you can tell it won't be totally internally reflecting. Let's now have a look at some questions to do with mechanics and materials. So figure 8 shows a cyclist going up a hill. The angle theta of the slope of the hill is constant. The total mass m of the cyclist and the bicycle is 65 kilograms. Write an expression for the component of the total weight parallel to the slope. Then the useful power output of the cyclist is 310 watts. The cyclist has a steady speed of 1.63 meters per second. Assume that the air resistance is negligible at this speed and calculate theta. So pause the video now, then unpause the video when you want to go through your answers. Right, so this question is asking you pretty much to work out the components of the weight. So what you would do is you would say that, well, weight is going to be acting down, so vertically down like so. So what you can therefore do is make your right angle triangle, and you'll see straight away that it's going to be give you that you've got your opposite and you've got your hypotenuse, so you can say it's going to be sine, because SOHCAHTOA, sine is opposite over hypotenuse, so therefore you know what the value is going to be for the weight, because if you look down, work down 65 kilograms, so the weight therefore of the force is going to be 65 times by 9.8, which is going to be 640. So therefore we can say that weight is equal to 640 sine theta. Now in the next part, what we can do to work out theta is we know that power is equal to force times by velocity. Why do we know to use that one? Well, we know from the question we are given the power output and we've got the velocity, so therefore we can work out quite quickly. We're going to need to work out the force here. So therefore you work out what your force is at that point. So P equals FV to work out the force. Therefore what you can do is you can work out through your value like so by doing, for example, you can work it out by doing 65G sine theta is working out to F. You can work it through like that and you get your answer to be 17.4 degrees. Now the next question says figure 9 shows an alternative zigzag path taken by the cyclist up the same hill. She maintains a steady speed of 1.63 meters per second. Discuss how her useful power output when taking the path in figure 9 compares with her useful power output in the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, so the important thing to note here is when you're taking the zigzag path, it's going to be a less powerful output, because what you can think about power is the work done per time. Now you're going to have the same work done, the same gain in your gravitational potential energy, because you're going to be doing the same ultimate change in height over in that particular time, but the time is going to take longer because you're going in a zigzag path, because your displacement is staying constant but your distance traveled has increased. So what's happening is you're gaining less energy every second, so therefore your power has gone down. The next question says, the cyclist reaches the top of the hill. She travels back down the hill in a straight line. The bicycle rolls freely without the cyclist pushing the pedals or applying the brakes. Figure 10 shows the variation of her velocity with time as she goes down the hill. So determine the acceleration of the cyclist 10 seconds after she begins to go down the hill. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you're trying to work out acceleration and you've got a velocity time graph. So with the velocity time graph, you know the gradient is going to equal the acceleration, but it's a curving line. So how do you work out the gradient of a curving line? Well, you draw the tangent, okay, to the point which you want to work out the gradient for, which in this case is 10 seconds. You then work out your gradient of the tangent, okay, and then work it through and you get 0.21 meters per second. Now again, it's very second squared. It's then very important that you draw on your tangent carefully and you draw very clearly in your answer your gradient triangle. The next question says, energy transfers occur as the cyclist travels down the hill. Outline how these energy transfers explain the shape of the hill in figure 10. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, what you've got to think about is as it goes down the hill, air resistance is going to increase with speed. So you can say for the resistive forces, drag is going to increase with speed. So energy is transferred from the cyclist to the internal energy of the surroundings by these resistive forces. Now you would say that initially you've got gravitational potential energy stored for your cyclist because it's high up, okay, but then that's going to transfer to the kinetic energy because it's then increased in speed as it moves down the hill. Now as the speed increases, less the gravitational potential energy will be transferred to kinetic energy as there's more resistive forces. So we can say that more will transfer to the internal energy of the air, and then at top speed the gravitational potential energy is transferred to the air or it's work done due to resistive forces because we're not going to be increasing in speed anymore, so no further energy is going to our kinetic energy store. The next question says, figure 5 shows the worker of weight 750 newtons on a uniform platform. The weight of the worker is acting at a horizontal distance d from end A. Throughout the question, assume the platform is horizontal and that all cables obey Hooke's law. The platform weighs 1,800 newtons and is suspended by vertical cables P and Q. Each cable has an unstretched length of 3 meters. The horizontal distance between P and Q is 3.6 meters. The worker moves to a position where the tension in the left-hand cable P is 1,150 newtons. Calculate D for this position. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, you've got to look very carefully and go, we've got a weight, we've got a distance, and it's balance. So we're going to be using the principle of moments. So what you can do is you can then look at what's the clockwise moments act on the object, what's the clockwise moments acting on the object, and then equal the two with each other. So what you can do is you can see that, look at the clockwise, okay, and look at the anti-clockwise moments, and you can work it out as such. So if you took your moments, for example, about B, you could say it's 1,150 times by 3.6. Why is that? Because you can see straight away that you've got your weight acting down there, okay, and you move to position where the tension is 1,150. Okay, so you do 1,150 times by 3.6, okay, equals 1,800, which is going to be, if you notice, the platform weight times by 1.8, because remember we assume the weight acting from the dead center. So if we're taking it from B or Q, therefore the distance from the center to one of the edges is 1.8. Then you'll plus 750 times by 3.6 minus D, because we're now doing the weight of the worker times by the distance it is from one of the sides. You can work it through there. So you can say 1,150 times by 3.6 equals 1,800 times by 1.8 plus 750 times by X. You can then work it all through, work out what X is, and it's going to be 2.4 meters. Right, the next question says, figure 6 shows how the extension of P varies with D as the worker walks slowly along the platform from A to B. The worker moves to a position X where the strain in P is 6 times 10 to the minus 5. Determine D for position X. Then the cable material has a Young modulus of 1.9 times 10 to the 11 newtons per meter squared. Calculate the tensile stress in P when the worker is at X. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? Well, you can see straight away that the extension is going to be 0.18 millimeters. How do you know that? Well, if you look through, you know what the value of D is going to be, okay, at position X, so you can work it out there, and then you can say, well, E is going to equal delta L over L, so therefore you can work it out, and then D is going to equal 1.8 meters. Then for the next question, we can say that the stress is going to be equal to 1.1 times 10 to the 7 newtons per meter. Again, because why is that? Well, we've got our strain, okay, from the previous question, 6 times 10 to the minus 5 there. We know that Young modulus is stress over strain, so therefore stress is going to be Young modulus times by strain. So you do 1.9 times 10 to the 11 times by 6 times 10 to the minus 5, and therefore you get your answer to be 1.1 times 10 to the 7 newtons per meter squared. The next question says, figure 3 shows a garden gate with a pulley system designed to close the gate. The pulley system raises weight A when the gate is open, and when the gate is released, A falls. The horizontal cable C passes over the pulley. The tension in the cable C causes the gate to close. Weight A is a solid cylinder with the following properties. Diameter is 4.8 times 10 to the minus 2 meters, length is 0.23 meters, and weight is 35 newtons. Table 2 gives the density of the 3 available materials. To use one of the 3 materials, which one of the 3 materials is used for A? So pause the video now, then unpause the video when you want to go through your answers. Right, so how to answer this question? Well, what you need to do firstly is you need to work out what the volume is going to be. So the volume is going to be equal to the area times by the length. So what we can do is we can then work out what our volume of A is going to be, because we can work it through by doing area times by length, and we get 4.16 times 10 to the minus 4 meters cubed. Okay, and that allows us to then work out what our mass is going to be as well, because we can say that, well, the mass is going to be the weight, which we got before, which is 35, divided by gravity, which is 3.6 kilograms. We can therefore say density is going to be equal to mass over the volume. So therefore we've got our mass, we've got our volume, we divide one by the other, and therefore we can work out which one's going to be the closest to, and we get our answer to be 8.3 times 10 to the 3, okay, which we can then work out to be brass, because it's very close to 8.6. The other way you could have possibly done it is you could have worked out your volume, worked out your mass, okay, for if it was particularly brass, for example, or iron or concrete, and then work it out to what the mass should be, and then see which is going to be the correct answer. The next question says, figure 4 shows the pulley arrangement when the gate is closed. Pulleys P and M are frictionless, so that the tension in the rope attached to A is equal to the weight of A. A weighs 35 newtons and the weight of the movable pulley M is negligible. Calculate the tension in the horizontal cable when the gate is closed. Pulley M is pulled to the left as the gate is opened. Explain why this increases the tension in horizontal cable C. So pause the video now. When you want to go through the answer, unpause the video. So how do you answer this particular question? So the first thing you've got to do is think about how you would calculate the tension in the horizontal cable C. So to do this, you've got to consider the tension. Now again, what you've got to realise is that the tension is going to be linking into the angle. So we would do 35 cos 55 because of the angle it's at, because it's in the horizontal. Now because there's 2 ropes there, you don't have to double that answer. So you have to do 35 cos 55, then multiply it by 2. Now it says pulley M is pulled to the left as the gate is open. So how will this increase the tension? Well, once again, what you're going to think about is the angle, because all it's asking about the component. So what would happen is the angle would decrease. So therefore, there's going to be a greater value of the force or the tension in the horizontal. So therefore, the tension in the cable must increase because there's more acting in the horizontal. Now the next question says, figure 5 shows a plain view with the gate open. The horizontal cable C passes over pulley R and is attached to the door at D. The angle between the door and the horizontal cable C is 12 degrees. The horizontal distance between the hinge and D is 0.95 meters. The tension in the horizontal cable C is now 41 newtons. Calculate the moment of the tension about the hinge. So pause the video now, then unpause the video when you want to go through your answer. Right, so how are we going to work this out? So what you've got to realise once again is that it's at an angle, so you've got to consider the component. So what you're going to have to be doing is you're going to have to work out the component of the force at right angles to the door. Now the angle you're given is not actually the one at right angles in that sense, so it'll be 41 cos 78, or you could do it as 41 sine 12, depending on how you want to work out your right angled triangle. So that gives our actual force not to be 41, as you might think in the question where it says that the tension is now 41 newtons, but rather the force that you would require is 8.5 newtons. Now moments are force times by perpendicular distance from the pivot, so it's 8.5 times by 0.95 meters, so your answer is 8.1 newton meters. Now the next question says, the same system is attached to an identical gate with stiffer hinges. Now the system does not supply a sufficiently large moment to close the gate. Discuss two independent changes to the design to increase the moment about the hinges due to the horizontal cable C. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important that when it says discuss, that means you've got to state what the change would be and explain why that would be the case. So you've got a couple of possible answers here. The first one would be to increase the weight or increase the tension. Now that would, because if you increase the weight, it increases the tension, therefore increases the moment. You could position the pulley a bit further out from the hinges, so therefore it would increase the angle, and therefore you'd have a greater component in the actual direction of the moment, so increases the moment. You could decrease the angle again by putting P and a fixed point closer together, so therefore would increase the tension, increase that force to increase the moment. Or you could move D further from the hinge and make C longer. Again, that would increase your perpendicular distance, so it would increase your moment. You've always got to think to yourself, the moment is the force times by the perpendicular distance. So if you wanted to increase your moment, you've either got to increase your force or you've got to increase your perpendicular distance between the line of action and the pivot. So you've got to think about how you could do that. We're now going to look at questions concerning electricity. So figure 11 shows a variable resistor has a maximum resistance 25 ohms. A sliding contact P is mounted on a thick copper bar. P can be set to any position between X and Y. Figure 12 shows the variable resistor being used to investigate the variation of current with voltage for a filament lamp. The normal operating voltage of the lamp is 12 volts. The 12 volt battery has a negligible internal resistance. The position of P is adjusted so that the reading on the voltmeter is at its minimum value at 0.75 volts. Calculate the resistance of the lamp when the voltmeter reading is 0.75 volts. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? Well, it's fundamentally a potential divider circuit. You've got to realise that because you can see there you've got your potentiometer in the circuit. So what you could do is you could use V equals R1 over R1 plus R2 times by V in. So what you could then do is work out that value, because you know what the resistance is of each one, you know the total resistance, you know the starting volts. So you see on here, you can see it's 12 volts there. So you can work it all through and you get your answer out. Okay, to give you your value for V, then you can work out what the value of the resistance is going to be. So you would get out ultimately 1.7 ohms, which is what the calculating value would like to work out. Or you could just do it as a ratio, because what you would know is that for a circuit, the potential difference is directly proportional to the resistance. So you could just ratio the values and work out your value as such like that. The next question says, figure 13 shows the variation of current with voltage for the lamp between 2 volts and 12 volts. Calculate the resistance of the lamp when the voltage across the lamp is 8 volts. Then explain in terms of electron movement why the resistance of the filament lamp changes as the voltage changes shown in figure 13. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work out the first one? Well, you know you've got current and you've got potential difference. So what you can do is you can read the values off the graph. So what you can see straight away is at 8 volts, what is the current going to be? Well, it's going to be 1.7 amps. So at that point, we can say V equals IR. So R equals V over I. So at that point, you can work it through and you get your answer to be 4.7 ohms. Now, in theory, because it's a curving graph, you could also do a gradient of a tangent which hits the point at the at 8 volts. However, you've got to be careful, it's the 1 over the gradient. You have to 1 over your answer if you did it by that methodology. The next question is asking to explain why the resistance changes. Now, it's important to note that as the potential difference increases, the current does not increase at the same rate. So therefore, the resistance is going up. So as the voltage increases, the current increases, and therefore increases more electrons through the wire. This then leads into what resistance fundamentally is, the collision between the charge carriers and the lattice ions. So there'll be more collisions between the electrons and the lattice ions because the vibration of the lattice ions is at a greater the amplitude. So the important thing to note is that the number of collisions every second between the lattice ions and the charge carriers increases. Now remember, it's always per second. It's the frequency of collisions that increases, which causes your resistance to increase. The next question says, figure 14 shows an alternative circuit used to investigate the variation of current with the voltage for the lamp. The circuit components are the same as in figure 12, when the voltage across the lamp is 12 volts and its resistance is 6 ohms. P is moved to position Y, calculate the total resistance of the circuit, then calculate the power transferred by the battery when P is at position Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you're going to do in this case is that if P is moved to position Y, straight away what we've got is we can work out our total resistance, and it's in a parallel circuit now. So it's 1 over R total equals 1 over R1 plus 1 over R2. At that point you can work out what your different values are, because we know that one resistor has a resistance of 6 ohms and the other one is 25. So therefore it's 1 over 6 plus 1 over 25. Add them together, flip it over to make it R. So you get 4.8 ohms out, which makes sense because it's in a parallel circuit and it's lower than any individual. Now what's the power transferred at this point? Well, we know that we've got R and we've got V. We know R we've just worked out to be 4.8 ohms. We know V from the question is 12 volts because that is the volts supplied by the battery. So we can do the equation from the equation sheet. P equals V squared over R. Pop in the values, work it out, and you get 30 watts. The next question says, a student wants to control the brightness of the lamp. He gives two reasons why the circuit in figure 14 is better than the circuit in figure 12 for controlling the brightness. The two reasons are that the figure 14 circuit can achieve a greater range of voltages across the lamp, and that the figure 14 circuit is more efficient at transferring energy to the lamp. Discuss without calculation whether either of these two reasons is correct. So pause the video now, then unpause the video when you want to go through your answers. So how would you work this through? So the idea is that there's a wider range, okay, in figure 14 circuit. Why is that? Because the voltage range in figure 14 circuit is 0 to 12 because we're using our potentiometer, whilst in figure 12 circuit it's 0.75 volts to 12 volts, and you can't get a value between 0 and 0.75. So when you're using it as a potentiometer, the important advantage is you can always get every value from 0 to the EMF of the power source. However, okay, the idea is that figure 14's has a lower efficiency than figure 12's. That's an important idea because at any particular voltage across the lamp, more power will be dissipated in figure 14 as any voltage across the lamp is always 12 volts across that resistor. So therefore it'll produce more heating. So therefore there'll be less energy going to the useful part of the circuit. So therefore it won't be as efficient. The next question says, a student assembles the circuit in figure 6. The battery has an internal resistance of 2.5 ohms. Show that the resistance of the 6.2 volt 4.5 watt lamp at its working potential difference is about 9 ohms, and that the terminal PD across the battery is 6.2 volts, and calculate the EMF of the battery. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you've been given the potential difference, you've been given the power, and you need to show that the value of R. So we can again say P equals V squared over R, rearrange that to make R the subject, and R equals V squared over P, pop the numbers in, and we get 8.5 ohms. Now how do you work out the EMF of the battery? So what you can do is you've got now your potential difference and you've got your resistance, so you can calculate the current in the lamp or the current in the 12 ohm resistor, or you can calculate the total resistance and then work out the total current. And therefore what we can then say is that EMF is equal to terminal PD plus loss volts, which is IR. So at that point, once you've worked out your current, okay, you can work it out by working it through by saying, well, what's the terminal PD? Well, you can work out what the terminal PD is because you can work out what the EMF, you can work out what the value is outside the circuit because you've got the working values there. So therefore you can work out your terminal PD to be 6.2 volts. You know what your current is because you can work it through to be 1.24 amps by working out the total current, okay, through the circuit, then adding them together. So you work the current in the lamp and the current in the resistor and add them together. Then you can times that by the internal resistance there, and then you get your answer out to be 9.3 volts. The next question says the student makes a variable resistor to control the brightness of the lamp. Figure 7 shows her circuit. She uses a resistance wire with a diameter of 0.19mm to make the variable resistor. A 5 meter length of this wire has a resistance of 9 ohms. Calculate the resistivity of the wire. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we've got here is we've got a diameter, we've got a length and a resistance, we need to work out the resistivity. So the first thing we need to do is work out our area, because if you look on the equation sheet, resistivity is equal to RA over L. So area is pi r squared, because we assume it's going to be a circular cross-sectional area for a wire. So therefore we work out our resistance is half the diameter, we put it into meters, so 0.19 divided by 2 times by 10 to the minus 3, and we work it out to be 2.84 times 10 to the minus 8. Pop the values into the equation and we get 5.1 times 10 to the minus 8 ohm meters. The next question says, figure 8 shows the 5 meter length of wire wrapped around a tube to make the variable resistor. Two plugs connect the variable resistor into the circuit. A movable copper contact is used to vary the length of wire in series with the lamp. When the contact is placed on the tube in one particular position, the lamp is dim. The contact is then moved slowly as shown in figure 8 to the right. Explain without calculation what happens to the brightness of the lamp as the contact is moved. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to understand is that if we move it to the right, the resistance is going to increase because you've got a greater length, so there's therefore more collisions between the charge carriers and the lattice ions. So if the resistance goes up, the current will therefore go down, so the brightness of the bulb will decrease. Or you could argue that there's a greater PD across the plugs, because we'll consider this as a potential divider, so the wasted potential difference is larger, so therefore the useful potential difference is lower, so therefore the lamp will be dimmer. The next question says, the student makes a different circuit by connecting the variable resistor in parallel with the lamp. The contact is returned to its original position on the tube as shown in figure 8 and the lamp is now dim. The contact is again slowly moved to the right. Explain without calculation what happens to the brightness of the lamp as the contact is moved. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, you've got to consider it's now in parallel. So what happens is the resistance will increase as you move it to the right, which reduces the current in the circuit and the battery. Or you could say it increases that external circuit resistance, so it reduces the potential difference dropped across the internal resistance of the cell. So therefore you've got a greater potential terminal PD because there's less energy being dissipated in the power source, so the lamp will be brighter. Let's now have a look at a few questions on further mechanics. So a teacher sets up a demonstration to show the relationship between circular motion and simple harmonic motion. She places a block on the turntable at a point 0.25 meters from its center as shown. The turntable rotates with an angular speed of 1.8 radians per second and the block does not slip. Calculate the time taken for the turntable to complete one revolution. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you've got to consider how you work out angular speed. Angular speed is the change in angle divided by the change in time. So we can rearrange this and we can say that time is equal to the change in angle over the change in speed. So therefore we know what our change in angle is in one complete revolution. It is 2 pi radians. So therefore do 2 pi radians over 1.8 radians per second to get 3.5 seconds. The next question says, figure 10 shows a plane view of the turntable and the block. The turntable rotates in a clockwise direction. Draw an arrow on figure 10 to show the direction of the resultant force on the block. The mass of the block is 0.12 kilograms. Calculate the magnitude of the resultant force on the block. Pause the video now, then unpause the video when you want to go through your answer. Right, it's always very important you're aware of the direction of the resultant force on an object moved with circular motion. Well, the centripetal force or the resultant force causing a circular motion always acts towards the centre of the rotation, so your arrow should be pointed to the centre of the turntable. Now we need to work out this resultant force, and there's a couple of equations we can use. We could use F equals mv squared over r, because that is just for a centripetal force, or we could use m omega squared r. Now if you think about it, we got m, so we could use either of them, but we've just been given in the previous question omega. We've got told 1.8 radians per second, and we got the radius as well, so we can use that to work out our answer to be 0.097 newtons. Now the next question says, describe with reference to one of Newton's laws of motion the evidence that a resultant force is acting on the block. Then the teacher adjusts the angular speed of the turntable so that the block completes one rotation every 2.50 seconds. She sets up a simple pendulum above the centre of the turntable so that it swings in phase with the movement of the block. Calculate the length of the simple pendulum. So pause the video now, then unpause the video when you want to go through your answer. So how do you answer this particular question? So you've got to understand what's causing a resultant force. Well, it's the idea that is if it's moving in a circle, well then the block is constantly changing direction. And the only thing that can cause an object to change direction or accelerate is a resultant force, which is Newton's first law of motion. And it's important to actually state what that law of motion is and link it into it. So at that point we must have, due to Newton's first law of motion, a resultant force acting on the object. Now to work out the length of this simple pendulum, what you've got to do is use your equation t equals 2 pi times by the square root of L over G. At that point we rearrange it and make L the subject. We've got t, we know 2 pi and we know G to be 9.81. So therefore we pop in our values and we get 1.55 meters. So it's very important you refer to your pendulum equation, which is given on the equation sheet. The next question says, a lamp is used to project shadow images of the block and pendulum bob on a screen. Both shadows appear to move with simple harmonic motion across the screen. Figure 11 shows the images on the screen in one instance. Initially the shadows move in phase with the same amplitude. Air resistance affects the motion of the pendulum, suggests the effect this has on the amplitude relationship and the phase relationship between the moving shadows. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to think about what's taking place. So if you have air resistance acting on the pendulum, well, the pendulum shadow amplitude becomes less because it's not going to move as much because energy has been dissipated out of the oscillator into the surroundings via this air resistance. And also the time period would decrease and the frequency would increase, so that would therefore give our phase to change. Now, it would, if you think about it, if the time periods and frequency remained identical, the shadows would remain in phase. Now, if you think about it, the time period is going to again decrease because the energy has been removed from the system. It is being damped in that instance. So, if we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you very much for watching this revision session on A-level physics for AQA, and it is on paper 1. So thank you very much for attending this revision session and have a lovely day.